Hi everyone. Today I will be presenting my project, which is a novel mantis shrimp inspired smart glove for stroke rehabilitation. So every year, 795,000 people in the US suffer from a stroke. The average annual cost of medication is $5,392. For me, this issue is personal. My grandfather had a stroke 27 years ago and lost function in his left hand. There are three current major rehabilitation technology, including air therapy, mental imagery, and robot-assisted rehabilitation. Mirror therapy and mental imagery are both promote neuroplasticity. However, their usability and effectiveness are limited, and it is passive rather than active. So, can we create an affordable and accessible solution for stroke patients? There are two types of material for robots, rigid and soft. Rigid robots are steady and strong, enough to provide support for the movement, but it is heavy, inflexible, and uncomfortable. Soft robots are light, flexible, and adaptable to all shapes of hand, and however, it is less stable and precise. There are three main actuators, pneumatic, electric, and cable-driven actuators. Depending on the material, the actuator may be different. This leads to my research question. How can we achieve a balance between accuracy and durability while maintaining lightweight and ensuring safety? A recent research from academia discussed a novel hybrid robot platform that integrates both rigid and soft arm. This hybrid system leverages the strength and flexibility of both rigid and soft robots, achieving enhanced dexterity and precision. I wondered if I could apply the same principle to address the durability concern of my robotics hand. The ergonomics of human hand are obtained with bones and fleshes, and then they are obtained with both bones and fleshes. Bones provide structural support and mechanical movement, while fleshes can adapt to fine motor skills and force transmission. Moreover, there are two types of bone. Osseous bones is hard and has high mechanical strength. Human bones are mainly osseous endoskeleton, which means that the bones are located inside of the body. The crustacean animals such as crabs and shrimp have a osseous exoskeleton, which means the bone is outside of the flesh. The cartilaginous bones are found in joints like your elbow. It includes collision and chondroitin and has a lower mineral content. It is soft and offers better flexibility and durability. Combining cartilaginous and exoskeleton ideas into a hybrid design for robotics hand allows the exoskeleton to provide support and strength while the soft outer shell is flexible. The goal is to develop a hybrid exoskeleton glove that can balance flexibility and durability with a cartilaginous exoskeleton structure. There are four stages of the development: finger design, structure design, hardware design, and results and experiments. So the inspiration of the finger structure is based on a mantis shrimp. The mantis shrimp's exoskeleton has a robust chitin outer layer and an inner layer that supports the structure and allows the rapid appendage extension. The shrimp striking mechanism requires protection and movement, which the segment design provides. The interior structure allows quick limb extension and retraction, while the exterior coating of the chitin protects the internal body. Mantis shrimp exoskeletons are segmented to allow body parts to move independently, giving shrimp extraordinary agility and the capacity to instantly adapt to environmental pressure. The final finger, which is on the right, looks very similar to a mantis shrimp. It has a silicone finger covering with a 3D printed jammy layer. In figure 1 and 2, it is the mold for the silicone finger. The outer shell shapes the finger and the inner shell is nudged into the outer shell to create a hollow section for inflation and deflation. The 3D printed jamming layer um, is filled with the gaps of the 3D printed jamming layer is filled by the silicone. And the silicone fills the gap between the semicircle, causing the finger to curl. And the final product has a green air nozzle to connect the air tube for the air to go in and come out, and it is attached with glue to the silicone finger. These are some technical challenges that I faced. The mold for the finger went through 20 iterations. In figure 8 is the figure 8 on the left is the first outer shell, with the board in figure 5 covering the outer shell with the inner shell in figure 3 being inserted in the mold. The mold could only be placed vertically to dry, as shown in figure 2 on the right. And placing it vertically made the silicone harden unevenly. So the round head in figure 1 is the solution to this problem. Now the mold could be placed horizontally to dry as shown in figure 1, and the thickness of the silicone became more even throughout the process. The second problem was the connecting with the air tube. So you can see here the bottom has a tiny hole, and that hole was for the tube to be inserted. And the second problem is that while the tiny hole left on the bottom didn't stick to the glue didn't stick to the silicone well, and the tiny hole made the demolding process extremely hard. And on the right bottom is the first version of the hand. The air tubes were connected by zip ties. The zip ties ruptures very easily, and it is hard for adjustment of the hand. Then I decided to left the whole bottom open, like here, and then to insert the green nozzle on the previous slide. And that makes it allows me to connect and disconnect the air tube. The durometer of the silicone was 20, which is not hard. The durometer of the silicone was 20, which is not too hard that it wouldn't expand, and it's not too soft that it would explode. The 3D printed material of the jamming layer was PLA, a relatively soft material that provides flexibility. And there is a pneumatic actuator that powers the inflation and deflation of the silicone finger. And all these designs are done on SolidWorks. The methodology and electric design. The glove has a Bluetooth connection. The user can select a finger or all fingers to rehabilitate on the app. The intensity of the rehabilitation is controlled with the air pressure and the curviness of the finger. The fixed rehabilitation mode updates the rehabilitation count, and the user can select the intensity. And the other mode is the intelligent rehabilitation mode. It has a preset intensity. Test and experiment I conducted. On the very left, it is the experiment of the N value. The N value is the number of segments dividing the jamming layer. The finger with very few segments or very dense segments weren't able to curl as well as the finger with the value in the middle under the same air pressure. So the result was 15 evenly distributed segments was the best with the best curviness. The next experiment compares the air pressure of a no-load pinky, wearing pinky, no-load index finger, and a wearing index finger exoskeleton, and when they're curled and uncurled. The air pressure is very similar throughout the entire bending process in all four situations. The peak air pressure is around 370, which is very safe, and the finger is fully inflated within 1.75 seconds. Which means that the device is very agile and reacts quickly. The finger holds more pressure as the finger curls, and it could hold around 1 kg, an object around 1 kg with all 5 fingers. The last graph compares the air pressure and pressure per grams. The behavior of the pressure on the graph are alike, which means that the air pressure changes the curvature angle of the finger, and as the air pressure gets As the air pressure gets higher, the finger curves more and the pressure also gets higher. The graph shows that the pressure per grams depends on the air pressure. So furthermore, I've integrated an AI system in the glove using a shared weight system to combine vision models with language. The camera on the glove will be able to identify the object using text image backbones to handle multi-scale picture elements. The system develops advanced AI algorithm for personalized rehabilitation plans and adaptive grasping tasks based on patient progress and biofeedback. In conclusion, my project successfully bridges the gap between flexibility and durability between in the robotics rehabilitation device by integrating a hybrid cartilaginous exoskeleton structure inspired by the mantis shrimp. Through the extensive prototyping and iteration, I have developed a novel soft robotic glove that combines silicone finger with a jamming layer controlled via pneumatic actuation and AI-driven rehabilitation modes. The result shows that the design achieves a balance between strength and adaptability, providing lightweight, comfortable, precise rehabilitation tool for stroke patients. The AI system enhances usability by offering personalized rehabilitation plans based on patient progress, which is affordable and accessible. And this glove has the potential to make rehabilitation more effective and widely available to those in need. Thank you for your time, and I'm welcome for any question you may have.